Hi, today we are studying evaluation of definite integrals type 3. Integrals of the form integral minus infinity to infinity r of x into e raised to ix dx, where r of x is a rational function such that degree of the denominator of r of x is at least 2 units higher than that of the numerator, and r of z has no real poles. That is, no poles of r of z lie on the real axis. Now we know that e raised to ix is cos x plus I sin x. Therefore, cos x into r of x is the real part of this r of x into e raised to ix, and r of x into sin x is the imaginary part of r of x into ix. Therefore, the real part and imaginary part of the above integral determine the important integrals integral minus infinity to infinity r of x cos x dx, which is real part, and integral minus infinity to infinity r of x sin x dx, which is imaginary part. Here r of x is coefficient of cos x and sin x respectively. Method of integration. Consider gamma equal to C1 plus CR. This is C1, where C1 is the real axis from minus R to R, and CR is the semicircle Z equal to R e raised to I theta, where 0 less than or equal to theta less than or equal to pi. Choose R so large such that gamma encloses all poles of R of Z in the upper half plane. Now integral over C1 R of Z e raised to IZ is integral minus R to R of x into e raised to ix dx. Because Z is real, we can choose the variable as s. So it is integral minus R to R of x e raised to ix dx. And when r tends to infinity, this integral is integral minus infinity to infinity r of x into e raised to ix dx. Now modulus e raised to iz equal to modulus e raised to I into x plus iy, which is modulus e raised to ix into e raised to minus y, which is bounded in the upper half plane, and degree of the denominator of r of z is at least 2 units higher than that of the numerator. So if we consider integral over CR r of z into e raised to iz dz, then here e raised to iz is bounded because modulus e raised to iz is bounded. So it is bounded, and degree of the denominator of r of z is 2 units higher than that of the numerator. So when r is large, this r of z is a quantity which is less than 1. Therefore, when r tends to infinity, integral over CR r of z into e raised to iz dz tends to 0. Therefore, integral over gamma r of z into e raised to iz dz equal to integral over c1 r of z into e raised to iz dz along this part plus integral over CR r of z into e raised to iz dz, that is along this part, which is integral over gamma, which is equal to, this integral is integral minus infinity to infinity this part r of x into e raised to ix dx, and this integral is 0. So integral over gamma r of z into e raised to iz dz equal to integral minus infinity to infinity r of x into e raised to ix dx when r tends to infinity. Now by residue theorem, integral over gamma r of z into e raised to iz dz equal to 2 pi I into sigma y greater than 0 residue of r of z into e raised to iz. Now integral over gamma, this part is same as integral minus infinity to infinity r of x into e raised to ix dx. Therefore, we get integral minus infinity to infinity r of x into e raised to ix dx equal to 2 pi I into sigma over y greater than 0 residue of r of z into e raised to iz. So you have to remember this part, integral minus infinity to infinity r of x into e raised to ix dx equal to 2 pi I into sigma over y greater than 0 residue of r of z into e raised to iz. Example: evaluate integral 0 to infinity cos x by x square plus a square dx, where a is real. We take r of x as the coefficient of cos x, which is 1 by x square plus a square. Then r of z is 1 by z square plus a square. Let I equal to the given integral 0 to infinity cos x by x square plus a square dx, which can be written as half of integral minus infinity to infinity cos x by x square plus a square dx, which is equal to half of real part of integral minus infinity to infinity e raised to ix by x square plus a square dx, and real part of e raised to ix is cos x. Therefore, this integral is same as half of real part of integral minus infinity to infinity e raised to ix by x square plus a square dx, which is equation 1. Now choose gamma equal to C1 plus CR, this C1 plus CR, where C1 is the real axis from minus R to R and CR is the semicircle Z equal to R e raised to I theta, where 0 less than or equal to theta less than or equal to pi. Choose R so large such that gamma encloses all poles of R of Z in the upper half plane. Then integral over gamma r of z into e raised to I z dz equal to integral c1 r of z into e raised to I z dz plus integral over cr r of z into e raised to I z dz. On the real axis, this is integral minus r to r of x into e raised to ix dx plus integral over cr r of z into e raised to I z dz, which is equal to integral minus infinity to infinity r of x into e raised to ix dx when r tends to infinity. So this integral becomes integral minus infinity to infinity r of x into e raised to ix dx plus this integral is 0 as we know from the theory, which is equal to integral minus infinity to infinity r of x is 1 by x square plus a square into e raised to ix dx. Now by residue theorem, integral minus infinity to infinity e raised to ix by x square plus a square dx is integral minus infinity to infinity r of x into e raised to ix, this which is equal to integral over gamma r of z into e raised to iz, which is equal to 2 pi I into residue of r of z into e raised to iz over y greater than 0. Now, to find the residue of r of z into e raised to iz, we know that poles of r of z into e raised to iz, which is equal to e raised to iz by z square plus a square, are zeros of z square plus a square. That is, z square plus a square equal to 0. That is, z square equal to minus a square. Therefore, z equal to plus or minus ai are the poles. Only here, only z equal to ai, which is a simple pole, which lies in the upper half plane. Minus ai lies in the lower half plane. Therefore, we only consider the pole at z equal to ai, which is in the upper half plane. Now, residue of r of z into e raised to iz at z equal to ai equal to limit z tends to ai r of z, that is e raised to iz by z square plus a square into z minus ai. This is because the pole is a simple pole. So we use the formula for that, which is equal to limit z tends to ai e raised to iz by this z square plus a square can be written as z plus ai into z minus ai into z minus ai. Z minus ai cancelled. Therefore, residue of r of z at z equal to ai equal to limit z tends to ai e raised to iz by z plus ai. Substituting ai, we get e raised to minus a divided by 2ai. Substituting this value in 2, we get integral minus infinity to infinity e raised to ix by x square plus a square dx equal to 2 pi I into this value. That is 2 pi I into e raised to minus a by 2ai, which is equal to pi e raised to minus a by a. Therefore, integral minus infinity to infinity e raised to ix by x square plus a square dx equal to pi e raised to minus a by a. Substituting in 1, that is here, we get I equal to given integral 0 to infinity cos x by x square plus a square dx, which is equal to half of real part of the evaluated integral. That is I equal to half of integral minus infinity to infinity cos x by x square plus a square dx, which is equal to half of real part of integral minus infinity to infinity e raised to ix by x square plus a square dx, which is equal to half of real part of pi e raised to minus a by a, and this is real. Therefore, we get pi e raised to minus a by 2a, which is the given integral or required integral. Thank you.